Welcome back. So in last class, we dealt with the Young Laplace equation, right? So Young Laplace equation was used to, determine the Laplace pressure for any given equilibrium. A geometry, in a equilibrium shape, or it can be used to describe the equilibrium shape of any given geometry. Okay, so in today's lecture, we will look at the application of Young Laplace equation, which is nothing but Kelvin equation. Okay, and we will see how Kelvin equation is used to describe the phase equilibria, wherein you can consider phenomena like boiling, condensation, crystallization, all that. So we will look at how Kelvin equation can be used, or how the curvature effect, affect the these phase equilibria, or the kinetics of, let's say, boiling and condensation, crystallization, etc. So in today's video lecture, we are going to look at the derivation of Kelvin equation, and then we are going to look at tutorial session followed by the derivation part. Okay, let's begin. Yeah, so first let's look at the Kelvin equation. So we know that we just now described that as such, Young Laplace equation is not applicable to phase equilibria. You cannot use that equation as such, to describe the the radius of a given geometry, especially in the application like phase equilibria, like boiling, condensation, and crystallization, right? But Kelvin equation helps us the find out the critical radius of the bubble, okay, and it also helps us find out the the pressure, right, of bubble or the droplet, okay. So in this equation, one can also describe how phase equilibria are affected by the what is known as the curvature effect. Okay, so this equation was proposed by Lord Kelvin himself. He is none other than the scientist who discovered the absolute the temperature scale. Okay, so in 1871 he proposed this form of equation, which we are going to derive shortly. So he in his article in 1871 he described using the application of Young Laplace. He proposed this equation. So let us look at how it can be appreciated. This equation can be appreciated, when it comes to the phase equilibria and a phenomena like boiling point, crystallization, and condensation, right? How the curvature effect is going to play a major role in these processes, right? So let's look at two scenarios. One is case one, where you have a flat interface, right? Case two, you have a curved interface. Now, so we know that because the curved interface brings in some amount of compactness, and therefore you can expect the pressure inside the bubble or droplet will be greater than pressure of at the flat interface when similar conditions prevail, right? So So in this case, let's look at the flat interface and the curved interface. So the vapor pressure of the curved surface is going to be greater than the vapor pressure of flat surface at any given temperature. Okay. So this condition is valid when the radius of the bubble is greater than the critical radius of the bubble. Okay. Right. So we look at how this curvature effect plays a major role and how it affects the phase equilibria. So let's say we have a case where boiling phenomena is occurring. Okay. So as the droplet size, we will see shortly in an equation using the Kelvin equation, as the droplet or bubble size goes down, the pressure goes up. Okay. So that I explained through the compactness of the bubble, right, just now. So as the vapor pressure of the bubble goes up, the boiling becomes easier, which means that the boiling, the kinetics of boiling, okay, evaporation can be improved if the bubble size goes down, right, which means that vapor pressure goes up. Okay, which is big. I mean, this is due to as the bubble size goes down, vapor pressure goes up, which can easily overcome the atmospheric pressure. Because it can easily overcome the atmospheric pressure, you can expect that this bubble can promote the boiling, okay, quickly. So this is actually quite useful. The curvature effect is quite useful if you want to accelerate the kinetics of boiling, right? Whereas on the other hand, the increase in the vapor pressure is not going to help in terms of condensation, because if vapor pressure goes up, it actually it doesn't favor the condensation, right? So in this case, curvature effect provide negative consequence. So one has to know, in this case, one has to understand that the bubble size one can tune so that the vapor pressure is not too high, right? Similar is the case when you deal with crystallization. Here also, as the vapor pressure goes up, you can expect that the solubility is favored. This is because of the high chemical potential that exists. That drives the solubility, to the greater extent. That's why the solubility will be favored when the vapor pressure goes up. The consequence of that will be crystallization will be less favored. So in the case of condensation and crystallization, increasing the vapor pressure is not going to help us, whereas there you need to tune such a way that the vapor pressure is not too high. Okay, so these are some of the consequences of curvature effect. So by knowing this, we can actually tune the size or the radius of the bubble or droplet, so that we can tune the respective process, right? So we are going to look at the derivation of Kelvin equation. In that Kelvin equation, you will see there is a relationship exists between the radius of bubble or droplet with the surface tension, okay, and the temperature, right? We will look at that shortly. Before that, let us list out the assumptions involved in this when deriving this equation. The first and foremost assumption that we need to know is this equation is derived keeping in mind the equilibrium exists between vapor and liquid, right? So the equilibrium established between vapor and liquid. That is the first and foremost assumption. The second one will be incompressible liquid. That you will know why we have to assume this, why we have to make this assumption. We will know that shortly when we derive this equation. The other one is the, in this case, we are going to take ideal gas, the fluid obeys the ideal gas. Okay, that is the assumption we are going to take. The last one is constant temperature, right? So these are the assumptions we need to note down, so that this equation is only valid in these circumstances, right? So as we know, the phase equilibria is our phase transition. Whenever we talk about, they are equilibrium process. At equilibrium, the chemical potential, the change in chemical potential in liquid side and change in chemical potential in gas side, both will have to be equal. This is the essential criterion of equilibrium. This we know, pretty much we know. So this is going to be our starting point. Now let's only look at the change in chemical potential liquid side. So if we look at the change in chemical potential liquid side at constant temperature, that is assumption we already have mentioned that. So in that case, you will not have the entropy term in this. So you will simply have the other term, which is VdP. So remember, this is nothing but molar volume. Okay, right? So this can be integrated using the limits, P naught to P. Here, this P naught is the reference state. Reference state for us in this case will be flat interface. Okay. So this is going from flat interface to at some pressure in curved surface, right? So this is our equation for the liquid side. So in this case, we know, since we mentioned that it is incompressible liquid, so we can treat V bar as constant 1, so that V bar can be taken away from the integral. So we will simply have P naught to P and dP. Okay. Now this is simply nothing but delta P, and this delta P is nothing but Laplace pressure. Okay. So we know Laplace pressure for a spherical geometry, because bubble or droplet always assume a spherical shape, right? So you can safely assume the geometry to be spherical in nature. And for that spherical geometry, the Laplace pressure that we know is nothing but 2 gamma by r. Okay, 2 gamma by r. I would say rs, which is the radius of the spherical bubble or spherical droplet. So in this case, so my simplified equation for chemical potential liquid side is going to be V bar into 2 gamma by Rs. Okay, this is my equation number 1. Now I know the gas side, I have the similar equation. Okay, right? Here also my integral limits going from P naught to P. P naught is a reference state, flat interface. P is the any pressure in a curved surface. Now V bar is molar volume. And here we also, look at our assumptions that we made in the beginning. So one of the assumptions we made was ideal gas. The fluid obeys the ideal gas. So in this case, you will simply have V bar is nothing but RT by P. So you can take the RT out, then you will have dP by P itself. So limit going from P naught to P. So you will simply have from the gas side, we will have d mu g is nothing but RT ln P by P naught. Okay, this is my equation number 2. So since we know at equilibrium, so we know d mu L and d mu G both will be equal. So then I can easily write the so ln P by P naught is going to be V bar into 2 gamma divided by, I will have RT into radius of the spherical. Okay, so maybe I can write the sometime you can replace V bar with if you know molecular weight and density, you can replace V bar as m by rho. In that case, we will simply have m into 2 gamma divided by rho into r into t into rs. So this is going to be the equation, okay, Kelvin equation. This is what we call it as a Kelvin equation, for the phase equilibria such as boiling, condensation, and crystallization. Now, so this is usually for a droplet. When we talk about bubble, until the critical size of the bubble, this particular when you evaluate this logarithmic, natural logarithmic, it will always be the fraction, which means that it will be negative, right? So P by P naught will be a fraction. In that case, it will be negative. So for bubble, this equation is referred to as it takes the minus negative sign. Okay, rest will be the same. Okay, rest will be the same, but the equation takes the negative sign because the radius of the spherical bubble cannot be negative, because the natural logarithmic is going to be negative as P by P naught is going to be fraction. You need to include this negative sign so that the radius of the bubble that we calculate will be a positive quantity. Okay, so the equation 3 is applicable for droplet. Equation 4 is applicable for bubble. Okay. Now what we can do is we can stop here, and now we can move on to the tutorial part. We have a couple of exercises. Okay. So we can look at them one by one. So we can look at them one by one. So let's say the equation that we know is the problem number 1, exercise number 1 is based on the Kelvin equation. Here we are going to calculate the vapor pressure of spherical water droplets of radius 1, 10 and 100 nanometer. So the temperature is given, which is 280 Kelvin, and the surface tension of water at this temperature is given 74.6 millinewton per meter. So now we know the equation, which is nothing but logarithmic of P by P naught, the ratio of pressure, okay, and molecular weight. M is molecular weight and rho is density. Okay, so all data required have been given. What needs to be calculated is the P, vapor pressure of spherical water droplets. Maybe you can list the P by P naught, okay, P by P naught for different bubble radius or droplet radius. So this we have got different droplet radius. Okay, when droplet radius is 100 nanometer, what is going to be my P by P naught is going to be, I'm going to directly write the answer for you. Maybe you can verify these answers yourself. So when the 100 nanometer droplet is given, the P by P naught for that case will be 1.011. For when the droplet radius is going to be 10 nanometer, then P by P naught will be 1.12, which is 1 order of magnitude higher than the previous one. And when the droplet radius is 1 nanometer, the P by P naught is 3.16. So if I look at this, when you change the droplet radius, down drastically, when it goes down, the P by P naught also, goes down. I mean, increases one order, increases drastically, right? You can see at least one order difference, higher than the previous one. So which comes to say that, which highlights the curvature effect of, droplet, right? So lower the droplet size, the P by P naught value will become higher and higher. As you go down, P by P naught, the pressure of the vapor pressure of the water droplet will become higher and higher, right? So this is one exercise wherein we can understand the application of Kelvin equation. In other exercise, we can even calculate the radius of the bubble, okay? So the radius of the bubble you can calculate using the equation that is nothing but 2 into m. M is here, since it is a water vapor, we can use m as 0.018 into the gamma value is given, which is nothing but 0.0585 divided by, we have the density, which is 957 into R, you have to take 8.314, which is given in joule per mole Kelvin. So, the spherical radius, the critical rate, the radius of the spherical bubble can be calculated in this way. Now, there is a condition given here. Calculate the minimum size for a bubble of water vapor forming 10 centimeter beneath the surface of water, right? So, which means that the condition is there is a bubble, okay? So, which is just below the water surface, but the height of this water surface is the bubble is kept below, 10 centimeter below the water, the surface. So you will have the bubble will have to overcome both the atmospheric pressure. So this will be water, right? This will be water. So it has to overcome both atmospheric pressure that is acting on the water, and then there is also called hydrostatic pressure, okay, which is nothing but H into rho into G, okay, and you have atmospheric pressure and you have the hydrostatic pressure, okay. So if you assume that your initial pressure is given, which is P naught is given, which is 108.8 kilopascal, but what we need to know is for this condition, so which means that the pressure, actual pressure for this condition, which is given here, which is atmospheric pressure plus the hydrostatic pressure, okay. So for this case, the pressure, actual pressure is going to be 102 kilopascal. Okay. So, if you substitute these values here, so we know that the P naught is 108, and so P is nothing but 102 kilopascal. So in that case, how we deal with it? So this will be 2 into 0.018 into 0.0585 divided by 957 into 8.314 into 375 into ln P by P naught. P will be 102 divided by 108, right? Okay. So if I substitute this value in P by P naught, the rest of the values are already known. So finally the radius of the spherical bubble is going to be 12 nanometer in this case, right? okay, approximately 12 nanometer. So you can understand for a given condition, the spherical bubble is going to be 12 nanometer. Remember, we have a negative sign here because of this fraction, which is logarithmic of this fraction is going to be negative, and minus, finally you will get the radius of the spherical bubble as a positive quantity. Here it is simply nothing but 12 nanometer. Okay, so I'm sure these exercises will help you understand the application of Kelvin equation much better way. So I will stop here. We will continue from the next lecture. Thank you.